Continuamos con la charla de Deep Reinforcement Learning de Vishal Bala. Vishal es ingeniero en Information Technology de la Universidad de Mumbai. Adelanta su máster en Computer Science en la Technical University of Munich en Alemania. Welcome, Vishal.
Nice to see you all. Thank you to the organizers for allowing me to speak here. Today, I will take you on a short tour of deep reinforcement learning. Hope you enjoy it. So before I begin the talk, I would just like to give I know she already introduced me, but a short introduction. So basically, I'm a master's student at the Technical University of Munich, and my major focus is on AI and NLU in specific. And I have applied a wide range of ML algorithms across automotive, robotics, and medical imaging domains. And currently, I'm interested in exploring deep reinforcement learning techniques for dialogue and NLU. And I would be happy to, I'm actually looking for collaborations and on challenging novel projects. So I can be reached at any of these four mediums through mail, LinkedIn, GitHub, or Twitter. So what's the agenda for today's talk? So first of all, I start off with the introduction. So basically, what's the motivation of using deep reinforcement learning? I'll also use it as deep RL just to make it quick. So after that, I'll touch base on the theory and concepts, which is like starts with reinforcement learning and then moving on to deep RL. Then we'll cover one specific use case, and then who are the key players in this field, and what are the toolkits available if you want to get started. And finally, at the end, I will also cover the limitations, challenges, and the research frontiers. And at the end, I would also share some additional links, tutorials, and references so that you can read later on. So let's begin. So what is the motivation behind using deep RL? So first of all, we have achieved like tremendous success over the last few years using deep learning. So deep learning is basically, for example, you can have a pattern recognition algorithm. So if you have a set of images, you can classify it, say, to cat, dog, or like any other different category. But the next frontier for AI is like much beyond this pattern recognition stuff that you are doing. So in this sense, deep RL stands out because we know for sure that deep learning is good for capturing our sensory information. For example, you can have like object detection, or you can have it for speech or machine translation. But reinforcement learning is good for like taking out complex actions. And in this sense, this combination or the synergy of deep neural networks and reinforcement learning, which is deep RL, is the next big frontier. So this was just one example where it started to learn, the algorithm developed by CMU started to learn how to play poker. And this mapping from sensors to action allows or subsumes both the control and action lane. And it is fascinating to see this is not just limited to games, but you can build like different applications based on it. So when was the first major breakthrough? So it was like last year when Google and DeepMind they created this software called AlphaGo, which used primarily deep reinforcement learning techniques, and it defeated the human in a game. I guess 4 sets to 1. And this was not just limited here, but also in the following year, that is this year, it teamed up with another player to have like a 2-player game. And what is interesting in this game, the number of possible moves in this game is very large. It's like more than the number of atoms in the universe. So we have kind of conquered one major game, which was like up till a few years from now quite difficult. So this was like a major breakthrough, and then you can see the applications ranging to other games. So this game is Atari. So basically, you see a paddle below, and the aim or the goal of the game is to hit the bricks above, and then you earn the points, and that can be seen on the top. These are your points, and these are the lives you lost. So You see a bit further, so this is like a training process going on. So after 400, it's just like kind of trying to stabilize and figure out how to play this game. And this is based on like raw pixels, so there's no information about the rules or anything of the game. It's just picking up the raw pixels. So here, after 600, there is like, it tries to find a good, or exploits a good strategy, wherein it tries to make a tunnel here, and then after that, it kind of figures out how to master this game. So it learned on its own, but this was kind of interesting. And this is again, as I said, like based on just raw pixels. So you just give the position of this and the ball and the screen. So yeah. So this is one application with respect to games. But as I told, this is not just limited to games. Oops. Yeah, so it's not just limited to games, but sorry, it's also shown potential in like robotics, dialogue systems, and marketing and other energy sectors as well. And here it's like one more example where it's trying to reduce some flexible behavior in a simulated environment. And the next frontier is like the competition is basically heating up, so they are not just trying out on simple games, but more complex games like StarCraft and Dota. And these are like the major players who are trying to work on this. So that's it with the applications. Now let's move on with the basic concepts. So let's start off with reinforcement learning. So basically, reinforcement learning was inspired by research into animal learning, and what makes reinforcement learning different from supervised or unsupervised learning is in unsupervised you don't have any labels. In supervised you have labels for your data, but in reinforcement learning there is no correct input label pairs. Like they are never presented, nor are the actions explicitly corrected. So when you try to fit a classifier, for example, in supervised learning, you will try to minimize the loss and try to adjust your classifier so that it predicts the correct labels. But here there is no correct labels as such. And the focus here is like on online performance. So it's used specifically in environments where you know the model of the environment, but there is no analytical solution possible. And also in cases where the only way to collect information from the environment is through interactions, or if there is no real world possibility, so you have like a simulation model. So reinforcement learning fits well in these kind of scenarios. So how does a typical RL scenario look like? So you have an agent and there's an environment. The environment is basically your problem domain or what you're trying to look for. So basically the agent is fed with a state information and also a reward information. This is at time step T. And based on what information it is given, this is called like observation. So based on whatever it has observed, it tries to make an action. And this action is fed back again to the environment. And this process loops back. So basically whatever action it took, it results into another state and another reward that is fed again, then the action. So basically in reinforcement learning, what we're trying to do is like maximize this future reward. And how we do this is by creating a mapping between the state and the action. So that is what is reinforcement learning in this slide. So how do you do this? So basically the underlying thing is a Markov decision process, which is a tuple. So that tuple has set of states S, set of actions A, set of probability, transition probability that is P, and then reward probability that is R, gamma that is a discount factor, and H that is a horizon. So it's 5 or 6 tuples. So what exactly is this P? P is the state transition model. So basically if you are in state ST, that is at time step T, and action AT, the next state is dependent on these two. So this is like the probability of getting into this state at T plus 1. And same goes with the reward probability, which is again dependent on the current state and the action. And it could be also seen in this diagram here. So basically, every state is only dependent on the previous one, and this is why it's like called a Markov decision process, because underlying is like a Markov property, which is just to take into account the previous state or the last history. And another important thing is this horizon, which is like till how long we want to consider the rewards. And this gamma is called the discount factor. It basically controls the importance of the future rewards. I will cover that in the next slide. Oops, I missed out. Okay, so also one more thing, important thing is like there could be this probability, the transition models could be deterministic or stochastic. So by deterministic, it means that if you are in state S3 and the action is 80, the next state would always be the same in deterministic, and same goes with the reward. But in stochastic, that happens in real world scenarios, this probability could change. Like instead of being in the same state as action, the next state could not be the same every time. You could have some variability there. Same goes with the reward. So that's stochastic. And in general, it is easier to formulate the problem in deterministic environment because it's easier to calculate and like derive stuff here, but stochastic makes it a bit more complex. So now we saw the basic of the tuple. So what exactly is the policy now? So basically, every agent has to perform this action when it's fed into some state and reward. So policy is basically the mapping. It's a function of the environment state, and it maps the state to the action. So basically, when you are given a state, you want to pick up the best action. So basically, that's your policy. So let's look at one example. So same gaming example. Here it's like a ping pong game, table tennis. So input are raw pixels, where you have the ball location and the location of the table tennis bat. And then the end result is whether to go up, down, or stay as at the same position. So this is your action and this is your input. So basically, in between lies the policy, which is like this hidden layer or neural network representation, which is the state to action mapping. So this is our policy here. So next up, what is reward? So agent's goal is to basically pick up the best policy that maximizes the total reward. So a naive approach would be just to sum up rewards at each time step. So it is here. But what happens in this case is if you have like infinite horizon, like this reward would be infinite. So that's why we introduce this gamma, that is the discount factor. And another important thing about the gamma, apart from that, the fact that it doesn't allow it to go to infinity, is that it gives preference to immediate reward. So the next reward would be highly weighted than the future rewards. And for another way to look at this would be, for example, consider this example. If you want a robot or a stick figure to walk, so what is your reward here? So basically, you can consider having his head position above the ground and also for a maximum amount of time. So if you can maximize this thing, that is your reward, like keeping the head position as high as possible from the ground and as long as possible. So that could be one possible way of formulating your reward in a real world scenario. So, yeah. So once you know the policy, how do you make the decision? Like, so one way is to you can try out different policies, and then for every policy you get a reward at the end, and then you will take the one which has like the largest reward. But what happens in this case is like this could work in like a very demo or a small application, but in general you have like large or infinite space, like so it's not possible to have such kind of approach, like a brute force approach. And more importantly, the variance of the sample. So for example, if you take a policy and the return is say 10, and in another case it is 100, so you don't know what is the actual return. So there is a lot of variance. So you need a lot of samples in this case to actually get a good figure or good number. So this makes it difficult to use this approach. So One way to come up with this is like to give some structure. And how do you give some structure is basically allow samples of one policy to influence or estimate the other one. So in our in today's talk, I would cover like two of these approaches. So before moving on to those two approaches, which are value iteration and policy iteration, I would like to cover like two basic types of reinforcement learning. So the first one is like model based. In model based, you already know the MDP, that is the Markov precision process, the whole tuple, the state, the action, the transition probability, and everything. So in this case, it's very good when you know it. You can do an offline planning. So you already know it, so you know what action or policy to take. So the examples are value iteration and policy iteration. But sometimes there is no information about the actual probability, the transition probability functions or the reward probabilities. But you know at least the initial states and the possible actions, but you don't know the transitions. In that case, it tries to iteratively improve itself online through interactions with the environment. And one such example is Q-learning. So this falls into model 3 approaches. So let's look at what exactly is a value function. So basically, value function is a measure of how good your state is. So it basically is given by this formula. So basically, it is an expectation over the total rewards, coming up on the rewards, and it depends on what policy you're choosing. So for example, if you take say policy 1 and then you calculate all the rewards to the horizon, so that is one particular value for that policy, and then you can have it for more number of policies. So at the end, if you do it for like large number of policies, at the end the optimal value function would be like a max over all the policies. But we are not just interested in how good the state is. We actually want the policy, which is the mapping. So you just take a hard max for this, which is just after you just get the which policy was it. So in value iteration, we are making use of this. So basically, it's like again an iterative approach. You start off with, so basically v of s is your value function. You assign it to some random values at the start, and then for all state and action, you try to compute it using this the previous formula, which is expectation. There is a slight notation mistake here. It should be v of s, not yes, I'll type this later. And then once you get it for all state and actions, then you take a max over them. And you do this until at one point of time there is no change, so it has converged. So it's an iterative process, validation, where you're trying to compute the value, the goodness of the state. And as you see here, like actually we are interested, if you see in this one. So we are at the end we are always interested in the policy. So here in value iteration, we are calculating the value and then we will take the max. But sometimes it's better to just calculate or compute the policy at the intermediate level as well. So you can redefine the policy at each step rather than calculating the value function. So and also both of these methods are proven to converge theoretically. So in policy iteration, you start off, you redefine the policy at each step and compute the value, and then you improve the policy, and you do this again until it's like it converges. I'll not go much into the detail here now. Maybe we can discuss later. So what's the basic difference or what are the similarities between a value iteration and policy iteration? So both have the knowledge of the MDP, which is used for offline planning. And policy iteration is like computationally efficient. It takes fewer iterations, but each iteration is like more computationally expensive. So these were like the model-based approaches. So now we look at one model-free approach, that is Q-learning. So it's like, again, we have the value function, which is the goodness of the state, but Q-learning is like quality of a certain action in a given state. So it can be given by this formulation where we have this Bellman equation. where we are estimating the quality function at for state S and action A, which is the immediate reward plus the, the maximum over all possible actions for the next state and action. And this is again an iterative algorithm because we don't have the MVP here, so we cannot do a offline thing. We have to iteratively improve our quality function. So basically, it's nothing but if you want to calculate it for times 50 and 80, it's the old value plus some learning rate. We'll touch what exactly it is a bit later. But it's the immediate reward and the discount factor into the estimate of the optimal future value. And basically, this alpha is how much importance you want to give to the old value. So, for example, if you put alpha as 1, this alpha is between 0 and 1. So, if alpha is 1, this term and this term cancels out. So, it is just a reward plus this. So, basically, it's just like your Bellman equation. But if this alpha is like 0.1, so that means you're giving high importance to the previous value. So you can set it based on that. And of course, it's also shown theoretically to converge and represent the true Q value. So that's it with some basic reinforcement learning stuff. Now I would like to move on to the next, which is basically RL stuff. But before I move on, if there is some question or I don't know, if you want to make it interactive or later on. Now or later on, okay. So basically, in the Q learning approach which we saw, which was like the Q function was for every state and action. So basic way to implement this would be like a table, but you cannot do this for like applications like for the example the Atari game video which we saw where it's trying to figure out the tunnel thing. So in that case, there is like if you have like 4 different screens and like 256 by 256. So these are the number of rows that would be in the table, which is like more than the number of items. So it's not possible. So how do you represent your Q function here? So one way is to represent it via function approximation using neural network, and this was how those guys at DeepMind figured out playing Atari and like many other games. And this was the initial version. There were like many other improvements over it, which was like double DQN, which connected some noise as this method overestimated the action value. Then there was a online version of it called delayed Q learning. Then you have other variants called greedy or speedy Q learning. I'm just listing this out. This is maybe too advanced now. So how does the deep Q network which they use look like? So it basically uses the game screen and the action as input. So basically you have the game screen and the action fed into the neural network, and then you get the Q value. But what problem is here is like you have for every possible action a Q value. But this is not good for when you want to make a forward pass. So basically, you will have to feed in both state and action. So an improvement over this was proposed, which was just to take the state and then output the Q value for each function, for each action. So this allows to give us just like a forward pass. Like you just put in the state, which is your game screen, and then you get a Q value for each action. So basically, how good is it to take a action say up based on say screen 1 of the state, or how good is it to take action down or to stay there. So to get a Q value for each action, and the input is just the state. So it makes it easier to have it in one forward pass. And another important thing in the neural network, so right now I've just represented this as a platform. So internally it uses convolutional neural networks because we are using the game screen, that is the raw pixels. But there is no pooling layer. I don't know if you're familiar. We use generally max pooling in deep learning or in CNN, especially CNN convolutional neural network. And the reason why we use max pooling most of the time is for object detection tasks, where you want to have some kind of translation invariant. So basically, if it's a face of a cat, it could be like rotated or scaled, or so we want to make sure to cover or capture that. So that's why we have max pooling. But in this case, we don't use any max pooling because in our game screen or the raw pixel input, we want to know the exact position of the ball or the bat. So in our case, we don't want any translation invariance. So the position is very important. So that's why there's no. This is a CNN, but there is no pooling layer in it. So apart from this, there is another approach called policy gradient. So every policy P has a large set of real value parameters, say Q1 to Qn, and we calculate the reward gradient. So basically, for each of these parameters, we calculate the gradient with respect to the reward, and then we update the corresponding parameter with this gradient value. So in a way, this approach is basically same as supervised learning, and in supervised learning, you have generally try to maximize the log probability of the actual label over the data set. But here in how it relates to or how is it same as supervised learning is basically you don't have the actual label y because we are dealing with a reinforcement learning problem. But we can substitute this y as a fake label, which is basically the action you took. So basically, if you're moving from state S1 to S2, you took a particular action, that would be your label. And then you can calculate this log probability, and this A is called the advantage. So this advantage could just be, for example, your reward. So if you took a correct action at the end, this could be like +1 or say +10. And if you took a wrong action, this would be -10. So at the end, you're trying to maximize the correct actions you took, so the log probability of the correct action, and minimize the log probability of the wrong action. So this is like a scalar number. And it is shown that this policy gradient approach is good, is a safe exploration technique and faster than value-based methods, which we covered a bit earlier. And it finds the locally best parameter, and it's good for policies which have a very high dimensional. So one more important technique which was developed in DeepRL was called as Actor-Critic. It is basically two different neural networks. One is called the actor, and the other is the critic. So basically, the critic's job is to estimate how good the value is at particular stage, and then the actor basically uses this information to take the action. It's basically two networks helping each other, and this helps to utilize the learned value function. And as you can see in this landscape, so basically you have these dynamic programming methods where we have this policy iteration and value iteration and Q-learning. And then you have like some policy optimization technique, which was policy gradient. And then this lies in between these two approaches. So it makes use of both these. It uses like the value function as a baseline, and also estimates the action based on the critic's estimate of the value function. So it's basically intermediate or makes use of best of both worlds. And another improvement over this was basically they tried to make it distributed. So basically it utilizes not just one Actor-Critic, but asynchronous. So basically it's utilizing multiple worker agents. And as you know, like with the distributed setup, you have like more speed up and diverse experience. But this is what is more important than the speed up. So basically, every agent will have its own environment. It will have its own set of network and like policy and tools. So basically, it is like a diverse experience in itself. So you're not just doing like multiple for the speed up or the thing, but it's like more diverse. So and it combines the benefits of both value and policy creation, and it is good for both continuous and discrete action spaces. So, how does this the whole life cycle is like this? So we have a worker, which is like a global network. It interacts with the environment, and then it calculates the, so each worker calculates the value and policy loss, and it sends the gradient from this loss to the global network, and then the global network updates it. So basically, intermediate is like working alone. Only thing that is given to the global network is the gradients from the losses, so that it updates it. That's it with the basics and the theory and concept. And next up, I will talk about one such use case, which is for dialogue systems. So, why does reinforcement learning first of all fit well in dialogue system? So, basically, in dialogue system or chatbot, you have a series of, for example, if you want to make a hotel reservation or book a flight, you can go online and search for specific location, and then the bot would respond you back with a series of options. So in this case, you don't know till the end what is your whether the dialogue ended properly. So what is whether it was like successful or not. So there is this delay reward concept which fits in here, and that's why you can use reinforcement learning techniques here. So let's look at this example. So this is just basically a Q&A bot. So you ask him which movie did Tom Hanks star in. Okay, so here you have deliberately misspelled the word movie and also star. Okay, so if it is trained well, it would know, okay, this is the same word movie and star. And but since it doesn't know what it means, so it asks back a question, what do you mean? And then you try to rephrase the question, and then it gives the correct answer. So this is like the correct answer. You give it like, so you are satisfied with the answer. So basically here, in this case, the reward is basically if your answer, you got the answer. So basically that's your reward. And if it is a wrong answer, you get like a negative reward. And these series of dialogue flow, these are our actions here. So in all the examples which I showed, they were mostly related to gaming. So in that case, your action was like up, down, or some movement of the joystick or stuff like that. But here your actions are basically these set of uh, questions or the flow of the dialogue. And another way to see this is the reward is not just based on the task completion. So you got the answer, so that's it. But you can have it based on your user satisfaction as well. So for example, if it took a long while to give you the answer, you could assign probably a less positive reward. But if it immediately gave you the answer, you could have a high positive reward. So you could tune the reward based on your based on the user satisfaction as well. So this is just a sample example. This was from Facebook AI research group and presented at ICLR this year, which is a new track or conference. So another use case is this by Maluva. They were acquired by Microsoft. They are based out of Montreal or Toronto in Canada. So basically, they first had some data set where they have some human responding to already queried questions, and then you have the answers. So that's your supervised learning part. So they train their uh, system based on some recorded dialogue. But you cannot just rely on the recorded dialogue because there could be some unforeseen scenarios where you want to try or where you want to answer the user query. So therein came in the RL part. And again, they use the Actor-Critic method, which I discussed shortly in the previous slides, for learning the new or the unforeseen situations. And they use some user simulation for training, and one advantage was there was like this infinite state space, and it was not just limited to the dialogue action, but also the slots inside the dialogue as well. Yeah. So that's it with the one such use case for data system. Now let's look at who are the key players. So basically, which group is doing research in this field? Who are the Twitter celebrities to follow, like to stay up to date? And also, what are the toolkits involved if you want to get started? So as you saw in most of the slides, like so they were like most of the stuff was done by DeepMind, like and then now you have OpenAI, and then apart from that, this Maluva stuff is like specifically for dialogue stuff, and then acquired by Microsoft, and then you have like Facebook and IBM Watson and stuff. Like so, um, so there is this group called BEAR, which is like Berkeley AI Research Lab. It's from the EU department of UC Berkeley, and also University of Alberta. So these are like one of the two main, like this is not like a comprehensive list, but two main labs that are doing active research. And apart from that, you have, so this is like some professors and researchers who are doing it. So it's like Professor Abhi, who had a boot camp last week in Berkeley itself. And then Richard Sudan is like author of the book called one of the founding fathers of reinforcement learning. And then you have folks from Google DeepMind, David Silver, who's lecturer at the must watch everyone. And then Vlad was author like many cool papers and put it all these shifted from neural networks to DeepMind from Google going to Google DeepMind now. And then you have like more people from OpenAI, like Julian, the co-founder, and then John, and then other people. And then other folks that were doing reinforcement and stuff is Mark Kisenberg and Jan Peter. And then this guy is doing like most of the dialogue stuff at Facebook AI research, research and as well. But this is not a comprehensive list, it's like just a few pointers if you want to get started. So what are the tools now? So basically, so you need not build all these algorithms from scratch. You have the implementation already there. So you could either use this OpenAI baseline or chainer reinforcement learning. I mean, these are just two of them. There are more, and they have all the high quality implementation of the reinforcement learning algorithms which we discussed. And apart from that, you have not just the implementation, but there is a set of environments. So basically, you have those games, the real world games. If you want to do some benchmarking or evaluation of your algorithm on that, so those are provided by OpenAI Gym and RL Lab. So this gives you like a head start if you want to test out something or you want to evaluate your stuff. So that is also available there. So next up is now we covered like most of the we went from the basic concepts to the advanced one, and then what are the toolkits and stuff. But there are still a lot of limitations or challenges in this field, and it's like a very growing field. So we'll cover some of them. So basically, in the queue function which we saw, you try to approximate that as a using a CNN, but there is a non-linearity when you use CNN or any neural network, and that is not stable and takes time to convert. So, for example, on GPU itself, it takes like a couple of weeks. So, one way of doing or overcoming workaround or a trick for that is to basically store some of your experiences in a not some all of your experiences in a replay memory. So basically, your experience is nothing but the state, action, reward, and the next state. So you should store this in a replay memory. And what is good in this case is basically you can sample some random mini batches from it. So basically, you make it like a supervised learning problem. So you already had some experiences. You try to use that for the next set of situations. And it also helps in breaking the similarity of subsequent training samples. And otherwise, that's how you avoid the local minimum, and then it takes lesser time to convert. And another problem was so for example, when the agent wants to learn the Q values, how much should it stay confident with what value, what number it has, or how much should it explore? So basically, it has a set of Q values at one particular time step. Should it use that every time for that action, or should it also try out some other action to that? So this is what is called exploration versus exploitation dilemma. So basically, exploitation is making use of what information you already have. If you're confident enough, you can make use of it again. But there should be some exploration also, because what is happening here is uh, in Q learning, you're just using a 3D exploration. So basically, when you're doing the maths, you just take the first action which gave you the highest reward. And then from next time onwards, you'll always use that. But there could be some better action as well. So we need some kind of exploration as well. So there is the fix or the trick here is to have a epsilon greedy approach. So what is this epsilon? So you first start out with an exploration. So basically you pick up a random action with probability epsilon, okay? And then or else you select an action according to the current key value. So basically this is your exploitation part with probability 1 minus epsilon. So what happens is at the start you can have this epsilon as high value. So at the start you have no information about the Q values. You are doing this iteratively. It makes sense to explore a lot at the start. And then as time goes by, you can decrease this epsilon value, because now your Q function or the agent has become more confident of using that Q function. So over time, it knows like which action should it exploit. So this is a fix of this problem. And another approach of deep RL, which is like another interesting area, is this called as evolution strategies. It has nothing to do with biological evolution, although the name suggests that, and the initial research was inspired by that. So you can consider this as a black box stochastic optimization technique. So you basically try to fit in n number of parameters to a single reward function, and then you try to tweak and guess iteratively. Uh, so what is the advantage over like the traditional RL techniques is basically there's no back propagation as was the case with the policy gradients or other stuff which we covered, and then it's parallel and robust. And also it's helpful for this credit assignment problem, and gives you like structured exploration. This is one another area of research which is going on, so to try out evolution strategies. And another variant of the normal technique is called like exploration with parameter noise. So basically, when you select some action, there could be some chance that you, say, for example, if a agent in a game wants to go uh, to, to the left, there could be some probability that it goes to some other direction. So you give in some noise at the action level. But another way of doing this, so this is your traditional thing. So you have an input, you have the state, and then when you're doing the action, you add some noise. Just to, so instead of adding the noise here, they inject the noise in the parameter space itself. So there itself it covers the variation of the randomness. So that is one another trick or some other research which is going on here in this traditional RL technique. And it's basically by doing this you are achieving something between the evolution strategy approach and the deep RL approach. So it's a kind of a middle ground. And apart from that, there is like a lot of work in, for example, these are the model-based RL approaches. So why we want to focus, why are people focusing on model-based approaches? So basically, if you know the model itself, you can do, as we saw, we know all the state transition probability and all the whole MDQ. So if we can find out the model itself, we can get more information, or it's easier to do all the calculation and stuff. So there's active research in model-based RL now. And another research area is basically how to find out the reward function. So that's called inverse RL, and it makes use of imitation learning and if you know of generative adversarial network. It has some concepts similar to that here. And as you know in deep learning, so first, for example, in a in a normal face detection algorithm, the first layer would detect some edges, then the higher layers would detect more complex features in your face. So you have a hierarchy of features. But in RL also, you can have a hierarchy of policies. So that is another active research area. And again, distributed approaches. So basically, you can have multi-agent RL, as was seen in the associated APC method. You can have multi-agent test. So here, the important considerations are how to exchange information in the network, or using the protocol buffer, or how to cover the communication aspects or the networking aspect here. And apart from that, you can also, the other research areas include memory and attention-based neural networks here, and then transfer learning so that you can transfer the knowledge of one learning model to the other. Uh, because at times it's not easier to get the whole model information for any application, so if you can make use of some existing model, so there's like some transfer learning research also going on here. And then again, some benchmarks and how do you evaluate and stuff. So, so to summarize, basically, now stable and scalable RL is actually possible. There are a lot of toolkits that are actively put in this area, and the examples which I showed you and some the videos which I showed you actually are proof of that. So where exactly was this deep network used here, like deep learning used here? So basically, they could be used for representing value, policy, or the model itself. So, and then the application is not just limited to gaming, as we saw in most of the slides, but it's also can be used for robotics, dialogue systems, marketing, healthcare, you name it, and you can come up with new applications as well. For example, I guess it's also used for algorithmic trading and finance. Right? But it's not as simple as you saw. Like there are a lot of hacks or tweaks to the traditional algorithms. Like you have to consider some other like experience replay or action daily approach and stuff like that. So there is still some research here as well. And much like how the agent rewards itself by observation, I hope today's talk was a rewarding experience for you all. I hope you got some pointers. And these are the references of some of the papers which I took pictures of the content from. And more importantly, I would like to share these additional links. So basically, we could refer these first to blog series. They are a good starting point if you are very new to RL or DeepRL. And then this particular blog on Bioluba is like for the data system approach. Then there's this 8-part series. Another good blog by Andrew Karkati is on this policy gradients. And then there was this another presentation slide which you can refer to. But if you want to get really deep into this field, it's basically to start with this book by Richard Sutton and Barto. It is actually it's available online as well, the draft, the second draft. And then this video series by Oxford Professor David Silver is also affiliated with Google DeepMind is a good start. And then this was some like the last month's tutorial at ICML, which is like the National Conference for Machine Learning in because it was in Australia. They had a tutorial there, and that was the slide. And then I was fortunate to attend the Deep RL bootcamp in Berkeley last week. So I put some of the things here that if you want, you can refer to this website again. So that's it from my side. Any questions?
Thank you, Michelle.
It is going to listening to find out how that did reinforcement learning can step in some applications. But I would like to ask, would you consider this an optimization model, what is optimization technique, or simulation iteration that leads you to an optimal point? And also, one more second question would be, this deep learning important will happen probably local or maximum, local points.
So, so to answer your second question, so you always do this over a number of episodes. So that solves your local minimum thing. So you train it like over different episodes. So that covers your that's the one way to make sure that it's not stuck in a local optimum or minimum of the mentioned. The first question, sorry, I forgot. You talked about some whether it's related to optimization technique or so basically, so I look at it this way, this is like based on my limited understanding. So in most cases where you don't have the model itself, so simulation-based approaches, you start off with this simulation-based approaches where the only possible way is to collect information through interactions. So in that case, if that is your application, it fits into the simulation-based stuff which you mentioned. But in other cases, I'm not sure, maybe there it could also fit in as a optimization technique. Uh, but in most other cases, where the model information is not there or there's like unclear or like half information and you try to get the information through interaction, in that case, it's like a simulation-based approach.
Hello. The question is, if I wanted to make it progress in Postgres, shall I have a specific knowledge on algebra or specific, or can I use a basic programming or mathematics? Can I make those tutorials, or I know have previous knowledge in machine learning?
So right now, like uh, so KNRL and the OpenAI Gym, they have like all the code is like in Python, for example. You can start that. So if you want to start up from like the coding perspective, you can start that, and then you develop like when you're trying to code, you search on the concept and then try to research on like read on what exactly it's trying to do. That is one way of doing it. So that is another. So I don't know if you know of this fast.ai. They have this like coding perspective. So they don't teach you the theory, but they teach you the coding way, and then based on that you learn the concept. But as such, there is now you can make use. There is no like actual tutorial which does this way, like to like a online course or something. But there is a lot of like code and like where you can start off with. So basic would be like Python, for example, or some linear algebra knowledge. You can start off with that. You need not be an expert in RL. Of course, it helps if you know the concept, but you can do the reverse way also. I think there's a question. Yeah, sure.
Okay. Vishal, do you know if deep reinforcement learning is what they're using to train their self-driving cars?
Yes, actually, yeah. So I think I mentioned in one of the application slides. I think I skipped over because the video was too loud. But yeah, so it's used for autonomous driving as well. So you have like end-to-end. So actually, if you in my slide I haven't mentioned exactly, but if you refer to I think this one, there is this. If you refer to the slides here, I think third or fourth slide has a picture of self-driving. So it's like used for lane detection or like tracking. But you can use for autonomous driving as well. So the applications are many.
The last question.
Okay.
Next slide.
Yeah.
Thank you. This is now an application of algorithm recommended for commanding systems.
So basically, you want to like give the user some like like some specific search item or like some. I'm not sure about the application of reinforcement learning here, but I think I can research and give you some. Like, as of now, I could just research on these 6, 7 applications that I listed, but I think I'm not sure like if it's used for recommended system. So if I come across, I can maybe tell you.
Thank you, Vishal. If you have some more questions, Vishal can answer in
Yeah, sure.
Slack, our Slack
Okay.
channel. And now we have the lips from pediatrics, and pieces already there. So.